Welcome to the Deep Dive, where we sift through the most impactful research and really bring you the concentrated insights. Today, we're diving into something truly revolutionary. Just think for a moment about your own brain. Every single day, it just effortlessly processes this torrent of information. You know, the sound of a busy street, the subtle shift in tone when someone's talking, recognizing a face you know in a crowd. It just gets it. You understand speech even if someone's mumbling or there's loads of background noise.
Yeah, it's incredibly robust.
Right. Now, compare that to even the most powerful supercomputers. They often really stumble with these exact same tasks. They struggle with the nuance, the ambiguity of human perception of natural language. There's this fundamental gap, isn't there, between how our biological brains learn and perceive and how even our most advanced machines currently work. So today, our deep dive is into a really cutting-edge breakthrough, one that brings us, I think, significantly closer to bridging that gap, closer to building machines that can learn and perceive like we do, but, with far greater efficiency.
Yeah, it's really about rethinking the basic building blocks of computing, taking direct inspiration from the brain itself. That's exactly it. The core problem we're digging into today is this inherent limitation of traditional computing. I mean, it's incredibly powerful, don't get me wrong, but it struggles profoundly with these complex, kind of ill-defined tasks. Things like speech recognition, image analysis, pattern identification, tasks where the human brain just excels.
Right.
So our mission in this deep dive is to explore a really novel approach, one that's directly inspired by the brain's architecture, its principles. And crucially, it leverages these revolutionary new materials. The idea is to usher in a new era of truly intelligent, energy-efficient systems.
Okay.
And we'll be focusing quite heavily on a key piece of research here, a paper from 2021 by Tathagata Paul and his colleagues. This work is, well, groundbreaking. It showcases an intrinsic learning capability, something called spike timing dependent plasticity, or STDP. Right. And they show this within an all-2D multi-state molybdenum disulfide, that's MoS₂ memory device, specifically for neuromorphic speech recognition.
Wow. Okay, that's a mouthful. MoS₂, STDP.
It is a bit dense, yeah.
Yep.
But the implications, they're potentially transformative for how we build AI.
Okay, so let's begin our journey maybe by looking at the very foundation of modern computing.
Where it all started, basically.
Exactly. I mean, for the better part of a century now, almost every single computer you've ever interacted with, your smartphone, these massive data centers, they've all been built on this really brilliant architectural concept, introduced by John von Neumann way back in 1945.
The von Neumann architecture.
Yeah, that's the one. And it's a design masterpiece in its own right. It's got this clear, dedicated separation between the processing unit, the CPU, right, doing all the calculations.
The brain of the operation, so to speak.
And then the memory unit, totally separate, which just stores all the data.
Simple concept. Super simple, but profound. And this design allowed for incredible flexibility. It's driven just unimaginable technological progress. It's truly a legacy to celebrate.
Oh, absolutely. The von Neumann architecture has served us incredibly well, no doubt about it. But it's also the source of this growing inefficiency.
Right.
Especially when we ask computers to tackle problems that involve processing huge amounts of data simultaneously, continuously.
Right.
Imagine like a brilliant chef trying to cook a really complex meal.
Okay.
In a von Neumann kitchen, every single ingredient, every pot, every pan, it's all stored in a separate pantry across the hall.
Okay, I see where you're going.
Yeah, the chef has to constantly run back and forth, fetching stuff, bringing it to the stove, doing something with it, then often taking it back to the pantry.
Or that running around. Exactly. This constant shuttling of data between the processor and memory. That's what we call the memory bottleneck or the von Neumann bottleneck. And it consumes significant time, huge amounts of energy, and ultimately it just limits performance. Now, this bottleneck, it becomes especially glaring when we're dealing with what we call these ill-defined constructs.
Ill-defined, like what?
Things like recognizing faces in a crowd, understanding a conversation in a noisy pub, learning from complex, messy data patterns. Our brains do this stuff effortlessly, right? Because in our brains, the pantry and the stove are effectively the same thing. Memory and processing are deeply intertwined.
Okay, so it's all integrated.
Precisely. For your everyday devices, this bottleneck is why they might still struggle with, say, real-time interpretation of complex voice commands, or why learning from new visual or auditory data still feels like such a heavy, power-hungry job for even the most advanced AI algorithms.
Yeah, my phone definitely drains its battery trying to understand me sometimes.
Right. The traditional architecture just isn't optimized for the kind of parallel, distributed, adaptive processing our brains naturally perform.
Okay, so if the von Neumann setup is that poor chef constantly sprinting to the pantry,
Yeah.
what's the brain doing differently? And more importantly, how can we engineer our computers to copy that remarkable brain-like efficiency?
Well, that's exactly where neuromorphic computing comes in. It's a really promising paradigm shift.
Neuromorphic, meaning brain-shaped
Hmm.
or brain-inspired.
Brain-inspired is probably the better term. This approach draws its direct inspiration from the architecture and the operating principles of the human brain. It aims to mimic its structure and, crucially, its functionality.
Okay.
And the goal isn't just raw speed for speed's sake, it's about fundamental energy efficiency. We're talking ultra low power consumption, inherently distributed processing like a huge interconnected neural network.
Like in our heads.
Exactly, and even a degree of fault tolerance. So the system can keep working pretty well even if some individual components fail.
That sounds useful.
It is, and the core concept driving all this is in-memory computing.
In memory. Computing where the memory is.
Pretty much. Integrating computation and data storage into the same physical location, blurring those traditional lines, much like how synapses in our brains act as both memory elements and computational units. And this integration, it isn't just some clever design trick. It's absolutely critical because it tackles that efficiency problem right at its root, especially for these specific brain-like tasks.
Right, the ones that trip up the old architecture.
Exactly. When traditional supercomputers try to solve these kinds of problems, they often just resort to brute force. They throw immense processing power and energy at them, which works for some things, sure, but it's incredibly energy intensive. It's expensive, and it's just not scalable to the kind of, ubiquitous, always on intelligence we envision for the future.
Like having smarts in everything, everywhere.
Yeah. Right. Neuromorphic computing, on the other hand, it seeks this elegant, energy miserly solution. It mirrors the brain's inherent design for parallel event-driven processing. Computation happens directly where the data lives, minimizing all that costly shuttling back and forth. It's really about being smart, not just powerful.
Okay, this sounds brilliant. Neuromorphic computing, in-memory processing. Why haven't we already built computers that think and learn just like us then? What's the holdup?
Yeah, it's a fair question. For a long time, the answer has been tied very deeply to our dominant computing material,
Yeah.
silicon.
Good old silicon.
Little silicon. It's powered the digital revolution, absolutely. But trying to implement these brain-inspired principles using silicon-based tech, well, you quickly run into some pretty significant roadblocks.
Like what?
Well, first, there are immense integration complexities. Trying to pack billions of tiny adaptive synapses onto a single chip is just incredibly hard with silicon processes. Then you've got problems like short channel effects. As transistors get smaller and smaller down near atomic scales, they start to get leaky, unreliable. It's a major headache.
Okay.
And crucially for brain-like efficiency, silicon devices tend to have high switching power requirements. They're energy hungry, especially when you need billions of them operating in parallel.
So silicon, despite everything it's done for us, just isn't the ideal material for mimicking the brain.
For this specific task, it really hasn't been ideal, and that really underlines the immense challenge here. Achieving brain-like scale and efficiency using conventional silicon. It's just tough. I mean, consider the sheer density and power efficiency of the human brain. It boasts an astounding synaptic density. We're talking approximately 10 billion synapses per square centimeter.
10 billion per square centimeter. That's mind-boggling.
It is, and astonishingly, it does all this complex processing with an energy budget of only about 20 watts.
20 watts. That's less than a dim light bulb.
Exactly. Now, silicon-based devices, despite all the incredible advancements, they really struggle to match that level of integration, power efficiency, and dynamic plasticity all at the same time. The fundamental electronic properties of silicon just make it difficult to create the kind of compact, low-power, continuously adaptive synaptic devices that are absolutely central to neuromorphic computing.
So the material itself is the bottleneck, in a way.
In many ways, yes. This fundamental material limitation is precisely why researchers have been working tirelessly, investigating alternative hardware platforms, searching for new materials that are inherently better suited to the brain's blueprint, pushing beyond the limits we've known with silicon.
And this brings us neatly to a really exciting development, one that promises to unlock completely new frontiers in computing. 2D materials.
The ultra-thin world.
Exactly. And these aren't just smaller versions of traditional materials, right? They represent a genuinely revolutionary alternative hardware platform, They offer unique advantages that potentially far surpass conventional silicon for these applications.
Hmm.
Imagine materials that are literally only a few atoms thick, like a single layer of graphene, for instance.
Atomically thin.
Right. This atomic confinement, meaning the electrons are basically forced to move in just two dimensions, it naturally suppresses those problematic short channel effects we talked about with silicon.
Which is a huge plus as devices shrink.
Definitely. It also leads to drastically reduced device footprints. You can pack an incredible number of components into a tiny space. And that's absolutely crucial if you want to build these ultra-dense, brain-like neuromorphic systems. But it gets even cooler, I think. The flexibility these materials offer is just phenomenal. You can stack different 2D materials layer by layer, almost like molecular Legos.
Van der Waals heterostructures, they call them.
Right. So you could stack, say, this molybdenum disulfide, MoS₂, with another material like hexagonal boron nitride, HBN, vertically, laterally.
Creating these tailor sandwiches at the atomic scale.
Exactly. And these layered stacks, they have incredibly clean, sharp interfaces between the different materials, which just opens up this whole world of possibilities for unique device designs, new functionalities that were simply unattainable with bulk materials. It's like having a completely new palette of building blocks for electronics.
And what's truly fascinating here is how these unique atomic scale properties allow these 2D materials to achieve functionalities that often genuinely surpass those of silicon-based solutions. Their ultra-thin nature isn't just about making things smaller, it fundamentally changes their electronic behavior.
How so?
Well, it makes them incredibly attractive for advanced electronics where you need really precise gate control, ultra-low power consumption, and super high integration density. These are all paramount for neuromorphic systems. So this really represents a significant step forward, pushing beyond the limits of conventional silicon, potentially enabling us to craft devices that are not only tiny, but also inherently more efficient and adaptable for these brain-inspired architectures.
And among this incredible family of 2D materials, one particular star player seems to be emerging in this field. Molybdenum disulfide, MoS₂.
MoS₂, yeah, it's getting a lot of attention.
It sounds like it. This is a material whose name you might start hearing a lot more in the coming years, I suspect. MoS₂ boasts this really impressive array of properties that make it exceptionally well suited for these new computing architectures.
What kind of properties are we talking about?
Well, things like a large intrinsic band gap, which is crucial for good semiconductor behavior, a high on-off ratio vital for telling the difference between a 1 and a 0, basically.
Clear signals.
Right. A near-ideal sub-threshold swing, meaning very efficient switching with minimal voltage. And high carrier mobility electrons can zip through it easily.
So good performance, good efficiency.
Exactly. You combine all those characteristics, and MoS₂ becomes, as the researchers put it, an ideal candidate for low-power in-memory computing applications for edge devices. Edge devices, meaning things not in the cloud.
Right. Small, localized devices, sensors in your smartwatch maybe, or your smart home speaker, things that need to process information efficiently right where they are, make intelligent decisions locally, and crucially, conserve power without constantly sending tons of data back to some massive server farm. MoS₂ looks perfect for that. Now, to really appreciate the breakthrough that Paul and his colleagues presented, it's helpful to understand the landscape a bit. What came before in terms of 2D memory devices?
Okay, what were people trying before?
Well, earlier research explored a few different avenues. For instance, some work involved using ionic liquids to sort of squeeze ions into materials like MoF3 or WSE2.
Ionic liquids. Sounds messy.
They can be. While they showed some promise for memory, they often prove to be quite environment sensitive. Their performance could degrade with changes in temperature or humidity, which makes them pretty unreliable for long-term, real-world applications.
Not ideal.
Not ideal. Other methods relied on defect-induced resistive switching, essentially creating controlled imperfections in a material, like HBN, to store data bits.
Deliberately breaking it slightly.
In a very controlled way, yes. But the problem was the variability of these defects. It made it really hard to precisely control the memory characteristics consistently across different devices.
Manufacturing headache.
Big time. And there were also some demonstrations of STDP using the formation of tiny copper filaments within MoS₂. This reduced the device footprint, which was good, but it often suffered from low on-off ratios, making the distinction between memory states less clear.
So lots of attempts, but with drawbacks.
Exactly. These shortcomings really highlighted a critical need. a need for a more robust, more precisely controlled, and inherently efficient mechanism for achieving this brain-inspired learning in 2D materials.
Okay, so this is where it gets really interesting, right? The researchers behind this specific paper, they designed a device that seems to overcome those previous limitations and truly leverage the unique properties of these 2D materials.
The core of it.
They call it an all 2D architecture with a floating gate FG MoS₂ device from a multi-layer van der Waals heterostructure.
Right, the Lego stack again.
Exactly. Now, a floating gate, that's like an isolated island for storing charge,
Yeah.
right? Crucial for memory.
Yes, it traps electrons or holes.
What makes this particular device so special, according to the paper, is that its entire operation, its ability to store and process information, is entirely based on tunneling of charge across the layers.
Quantum tunneling.
Yeah. Imagine electrons literally passing through an incredibly thin, sort of invisible quantum barrier rather than flowing like current in a normal wire.
Exactly. And the key innovation here, the real game changer, is the intrinsic capability of this single solid-state MoS₂ floating gate transistor to directly model spike timing-dependent plasticity STDP.
Okay, back to STDP. Intrinsic capability, meaning it just does it naturally.
That's the idea. This learning mechanism is basically built directly into the physics of the device itself.
Ah,
And this is monumental because it circumvents the requirement of any other separate learning circuitry.
so you don't need extra bits on the chip just to handle the learning part.
Precisely. Traditionally, if you wanted to implement a brain-like learning rule like MTDP, you often needed additional complex transistors, external logic gates, maybe dedicated circuits, just to manage how the network adapts and learns over time.
Adds complexity, adds power consumption.
Hugely. By embedding this capability directly within a single MoS₂ floating gate transistor, these researchers have drastically reduced the hardware complexity. They've significantly lowered the potential power consumption. And they've given the device this inherent self-contained learning capability. Think about it. This isn't just a memory cell anymore. It's effectively a self-learning synapse.
A learning synapse on a chip.
Yeah. And this moves us beyond those previous 2D material-based floating gate memories that were largely restricted to just acting as passive memristors, basically just analog memory behavior. While there were some earlier demos of STDP, for instance, in carbon nanotube FG transistors, they often needed extra transistors or pretty complex setups to get the full functionality.
Okay.
This work, by contrast, shows STDP as this intrinsic, almost elegant property of a single MoS₂ FGFET. And that makes it a truly profound step forward for brain-inspired computing hardware.
Okay, that's a huge leap forward as self-learning synapse. But to really get our heads around it, we need to understand how it learns. You've mentioned spike timing dependent plasticity, STDP, a few times now. Can you break that down for us? What exactly is STDP?
Absolutely. Think of STDP as one of the brain's fundamental rules for learning and memory formation. It's what we call a biologically plausible learning rule.
Meaning, it seems like something the brain actually does.
Exactly. And it dictates how the strength of a connection, the synapse between two neurons, actually changes over time. And the core idea is beautifully elegant in its simplicity. The change in synaptic conductance, which is basically how strong or weak that connection is, depends critically on the time difference, the delta, like ducta or ASHT.
Okay, the timing.
The timing between a presynaptic spike, that's the incoming electrical signal from the sending neuron, and a postsynaptic spike, which is the output signal, the firing, of the receiving neuron. So, to elaborate on the rule itself, if an incoming presynaptic spike consistently arrives before a postsynaptic spike.
Input before output.
Right. And crucially, it has to be within a very narrow time window, typically just a few milliseconds in biology.
Right.
Then that particular synapse strengthens. This process is called potentiation. It's like the brain saying, hey, this input clearly helped cause this output, so let's make this connection stronger for next time. Makes sense, right?
It reinforces useful connection.
Exactly. Conversely, if the postsynaptic spike happens before the presynaptic spike, meaning the output neuron fired, without that particular input being a direct cause just before it have, then the synapse weakens. This is called depression, and it helps prune away connections that are irrelevant or not helpful.
Gets rid of the noise.
Sort of, yeah. This precise temporal order is what makes STDP so powerful. And if you connect this to the bigger picture, this is a fundamental mechanism for how our brains learn from repeated experiences, how we reinforce effective neural pathways, how we forget what's unimportant. It allows us to adapt, form habits, and continually get smarter and more efficient over time. It's truly learning by timing.
Okay, so that's how our brains seem to learn. How did these researchers actually manage to observe this sophisticated, timing-dependent learning behavior in a tiny atomic-scale MoS₂ device? Seems like a huge jump.
It was a meticulous experiment. They set up their MoS₂ floating gate field effect transistor, the FGFET, very carefully. They configured its gate and source terminals to effectively act as the pre- and post-synaptic terminals, respectively. Just like you'd think of a biological synapse having an input and an output side.
Okay, mimicking the structure.
Exactly. And then, to test its learning capability, they didn't just zap it with standard square electrical pulses. They used what they called biorealistic pulses.
Biorealistic, like brainwaves.
Sort of. The electrical signals they applied closely mimicked the shape and timing of action potentials, the spikes that neurons actually use to communicate in the nervous system, those sudden, brief changes in voltage.
Okay, using brain-like signal.
Yes, that was essential. To see if the device could truly respond in a brain-like way to brain-like inputs. And what they observed was, frankly, groundbreaking. The channel conductance of the device representing that synaptic strength, it genuinely increased for positive freeze values.
Pre-spike before post-spike. Stronger connection.
Exactly. And conversely, the conductance decreased for negative reef values, where the post-spike came before the pre-spike, weakening the connection.
Just like the biological rule.
Just like the rule. What's more, they found that the amount of change, the strengthening or weakening, was larger for smaller time differences, and it decayed as the time difference got bigger. This precisely mimics the nonlinear, sort of exponential decay characteristic observed in biological synapses under STDP protocols.
Wow.
If you look at their paper, there's a graph showing this exponential reduction in AG%, with increasing AG% being the percentage change in conductance. It's a beautiful mirror image of biological STDP.
So clear proof of concept.
A very clear demonstration of active, timing-dependent learning embedded directly within the physics of the device itself, not just passive memory storage.
That's incredible. A material inherently learning just based on the timing of signals. But how?
Yeah.
How does an incredibly thin atomic scale material actually do this precise timing-dependent learning? It's not like there's a tiny brain inside, right?
Yeah.
You mentioned charge tunneling earlier being key. Can you unpack the physics behind how this learning actually happens?
Yeah, it's a really beautiful intersection of quantum physics and clever device engineering. The microscopic origin of this plasticity, this learning, lies in what's called electric field-driven tunneling of charges. These charges can be either electrons or holes, depending on the setup, and these charges tunnel from the MoS₂ channel layer to the floating gate layer, flowing across that ultra-thin HBN tunnel barrier separating them.
Tunneling, like phasing through a wall.
Kind of. At the quantum level, electrons can pass through an energy barrier that, classically, they shouldn't have enough energy to overcome, especially when you apply a strong enough electrical push, an electric field. This specific type of tunneling follows what's known as the Fowler-Nordheim mechanism, or FN tunneling.
Okay, FN tunneling. Got it.
Now, the key ingredient for this tunneling, and therefore for the learning, is the overlap potential.
Overlap potential.
Yeah, think of it as the combined electrical force or voltage that exists across that HBN barrier, because the presynaptic and postsynaptic spikes arrive at slightly different times. Their electrical fields overlap briefly.
The timing difference creates a specific voltage overlap.
Exactly. And charge tunneling, which causes the change in synaptic weight, only happens when this overlap potential gets above a certain critical threshold. So, for instance, when a presynaptic spike arrives just before a postsynaptic spike, that's positive ERO, it creates a specific potent overlap potential across the HBN layer. If this potential is strong enough, it effectively drives electrons from the MoS₂ channel to tunnel into the floating gate where they get trapped.
Storing charge on that floating island.
Right. And this accumulation of charge on the floating gate then modulates the conductivity of the MoS₂ channel underneath it. It effectively increases its conductance, strengthening the synapse.
Makes it easier for current to flow next time. Potentiation.
Precisely. And for negative weight, the reverse timing reverses the overlap potential. This might lead to charges moving in the opposite direction, maybe holes tunneling or electrons being expelled from the floating gate. The net result is a decrease in conductance, depression.
So the timing directly controls the charge movement via tunneling.
Exactly. And crucially, the researchers' numerical simulations of this STDP response matched up really well with their experimental data, which strongly confirms that this electric field-dependent FN tunneling is indeed at the heart of the observed STDP behavior. It's a fantastic example of fundamental physics enabling complex, brain-inspired functionality.
That's a crucial detail. It's not just an observation, but the underlying quantum mechanics are well understood and actually modeled. That adds a lot of confidence. And you mentioned earlier the STDP timescales they observed, around 100 microseconds, are faster than the typical millisecond timescales in biology.
Yeah.
But the researchers also pointed out something important, that these timescales are tunable by changing the spike parameters. So it's not like it's locked into that speed. It can be adjusted, which sounds incredibly useful for engineering purposes.
Absolutely. This tunability is a significant advantage, especially when you think about practical applications. The researchers demonstrated exactly how they can tune this STDP response. It's actually quite straightforward. By simply increasing the amplitudes of the pre- and post-synaptic spikes, basically just making the electrical signal stronger.
Turning up the volume, so to speak.
Kind of, yeah. The magnitude of that overlap potential we just talked about also increases. This, in turn, leads to a larger tunnel current. More charges get pushed across that HBN barrier.
Okay.
And the consequence of that is a greater overall change in conductance, a stronger learning effect. And this change also persists for a wider range of Uretnat values. It effectively stretches or compresses the learning window of the device.
So you can make it learn faster or slower, or be sensitive to shorter or longer time differences.
Exactly. They achieved an impressive timescale tunability over a factor of 5 just by tweaking the pulsing amplitude. And what's particularly fascinating here, and a real plus, is that this pure electrostatic operation, it's all driven by electric fields, offers a profound advantage. It opens up the possibility of engineering tailor-made STDP responses for specific applications.
LR-made learning.
Yeah. Imagine being able to customize a device's learning speed and sensitivity. Maybe you want a rapid learner for quick, dynamic pattern recognition in, say, a drone's visual system.
Right.
Or maybe you need a more deliberate, precise learner for analyzing complex, slowly evolving medical data in some diagnostic tool.
Okay, different learning styles for different jobs.
Precisely. That level of fine-grained control over how a device learns is incredibly powerful and offers immense design flexibility for future neuromorphic engineers.
Okay, this inherent tunable learning capability in just a single tiny MoS₂ device is incredible in itself. But, how do you actually use it? How do you put it to work? To demonstrate its practical utility, the researchers didn't just stop at characterizing one device. They went ahead and built an entire neuromorphic speech recognition system, or NSRS. And it's directly inspired by the human auditory pathway. They essentially engineered a kind of neuromorphic ear.
Yeah, it's a fantastic example of biomimicry taken right down to the hardware level. And to really understand their system, it helps to briefly remember how our own biological ears work. It's quite amazing, really. The human auditory pathway starts with the cochlea, this incredible fluid-filled spiral structure deep inside our inner ear.
The snail shell thing.
That's the one. Its main job is to convert incoming acoustic signal sound waves into a time frequency map, basically a spectrogram of the sound happening over time. It does this by transducing mechanical vibrations into waves that travel along a special membrane called the basilar membrane. This movement then excites tiny inner hair cells, which in turn release neurotransmitters chemical signals to the primary auditory neurons, generating electrical signals or spikes.
Converting sound to electricity.
Exactly. After this initial conversion and filtering, these signals travel along the auditory nerve up to the primary auditory cortex in the brain. And that's where the higher level processing happens, crucial feature extraction, pattern recognition, and of course, learning to understand the sounds.
Right.
The NSRS they built aims to emulate these fundamental stages of human hearing.
So they basically translated that biological blueprint into a 3-block architecture for their NSRS. You can actually see a diagram of this in their paper. Can you walk us through each of these key pillars of their neuromorphic ear?
Sure thing. The first block is the cochlea model. Specifically, they use the CAR-R part of a well-known computational model called CAR-Fake. It's designed to mimic the auditory periphery.
Mimicking the first stage of hearing.
Exactly. Its function is to meticulously mimic the behavior of the basilar membrane, the inner hair cells, and the spiral ganglion cells, or SGCs, in our ears. It takes raw audio samples as input, and then through a series of pretty sophisticated filtering and nonlinear steps, it converts them first into that spectrogram, the detailed time-frequency map,
Okay.
and then into spike trains. These are sequences of electrical pulses, like Morse code for sound, using a statistical method called a Poisson process for the SGC output.
Spikes representing the sound features.
Right. For their system, they implemented a 54-channel SLIR model. Think of it like 54 tiny filters, each tuned to a different frequency band. These extract frequency components within the range of 100 hertz up to 4 kilohertz, which is a really crucial band because it captures most of the essential information in human speech needed to distinguish different words and sounds. Okay, the second block. This is arguably the most innovative part, the unsupervised feature learning stage.
This is where the MoS₂ comes in.
This is exactly where our MoS₂ floating gate transistors get to shine. They are implemented here as multi-state memory with inherent STDP learning capability.
So each OS2 device is one of those learning synapses we talked about.
Precisely. In this stage, the synaptic connections between the input, those Poisson neuron spikes coming from the Coakley model, and a set of 16 integrate and fire IF output neurons, they actively learn the important acoustic features in the sound.
Integrate and fire neurons. They just add up inputs until they pop.
That's a good way to put it. It's a simplified model of a biological neuron. It accumulates incoming electrical signals, and if its total potential reaches a certain threshold, bang, it fires, generates an output spike. Now, the learning mechanism here uses a clever winner-take-all strategy for updating the synapses.
Winner take all, like a competition.
Exactly. Among those 16 output neurons, the one that achieves the highest membrane potential and fires first is declared the winner for that moment. It then gets to update its incoming connections based on those STDP characteristics we discussed, strengthening connections that contributed to its win. And importantly, it then enters a brief refractory period, so it can't fire again immediately. This gives other neurons a chance.
Okay.
And crucially, there are also inhibitory connections among the IF neurons. This ensures competitive learning. It stops them all from just learning the exact same feature. Instead, they specialize in detecting different patterns in the sound.
So they carve up the learning task.
Right. And the really profound key insight here, the big deal, is that this stage learns these features in a completely unsupervised manner. It learns directly within the MoS₂ FGFT memory itself without needing any additional external learning circuitry.
No separate training chip needed.
Nope. This dramatically simplifies the system's design and significantly reduces its power requirements compared to traditional approaches. Okay, finally, the third block is the simple linear classifier. Its function is pretty straightforward. Just classify the spoken digits, 0 through 9 in this case, based on the distinct features that were learned and extracted by that previous MoS₂ base stage.
So taking the learned features and making a decision.
Exactly. The method they used involves taking the accumulated postsynaptic potential, or PSP, which is basically the summed electrical input and internal state of all 16 of those IF neurons from the feature learning stage. This accumulated information, representing the learned patterns, then feeds into a standard machine learning algorithm called a linear support vector machine, or SVM, classifier.
In SVM, that's a pretty standard tool.
No. It is. And the beauty of this whole approach is that because the MoS₂ devices have already performed such effective unsupervised feature extraction, a much simpler classifier, like a linear SVM, is sufficient. You don't need the kind of super complex, multi-layered classifier you typically find in traditional end-to-end supervised deep neural networks.
So the cleverness is baked into the MoS₂ learning stage.
A lot of it, yes.
That's a really beautifully designed system, isn't it? Mimicking the brain's efficiency all the way from sound processing to unsupervised feature extraction and then a simple classification. But the proof's in the pudding. How did it actually perform? What were the results when they fed this neuromorphic here real speech?
Yeah, the results were actually quite impressive, especially considering this is a proof of concept system demonstrating a completely new learning paradigm with novel hardware. They validated the NSRS using isolated spoken digits from a well-known benchmark dataset called the T-digits database.
T-digits, okay.
The comprehensive collection contains about 6,520 audio recordings of digits 0 through 9 spoken by various speakers. So a good test set.
And the accuracy.
After training, that relatively simple linear SVM classifier achieved an impressive 88.92% accuracy on the unseen test set.
Nearly 90%. That's for recognizing spoken digits with this new tech.
It is good, but maybe even more insightful than just the headline accuracy number is understanding what the system actually learned during that unsupervised phase.
Right. Did it learn meaningful things?
It seems so. The researchers analyzed the learned synapses, the final conductance states of those MoS₂ devices, and they found that these learned weight patterns were remarkably similar to the original spectrograms of the different speech sounds.
So the synapses captured the sound pattern.
Exactly. It's a critical point because it indicates that the MoS₂ FGFETs, guided by STDP, effectively extracted crucial speech formants, those characteristic resonant frequencies that help us distinguish different speech sounds. For example, they showed that some groups of the IF neurons ended up strongly connected to inputs representing high-frequency information, which was characteristic of digits like 2, 3, and 8. Meanwhile, other groups of neurons specialized, capturing the energy patterns for digits like 4, 5, and 9, which have more energy in different frequency channels.
So different neurons specialize for different digit sounds.
Precisely. This clearly demonstrates that the synapses learn distinct, meaningful patterns that could effectively differentiate or group the different digits, much like how our own auditory cortex learns to distinguish sounds. They also use tools like a confusion matrix, which shows where the errors happen, like mistaking a 1 for a 7 and a TSNE visualization.
TSNE.
It's a clever technique for visualizing high-dimensional data in 2D or 3D. Their TSNE plot showed really distinct clusters forming for the different digits based on the learned features. This visually confirms that the system successfully extracted discriminative features. It really proved the unsupervised learning worked effectively.
Okay, that's a truly significant achievement then, showing the system can learn to differentiate spoken digits using this intrinsic STDP in a MoS₂.
Yeah.
But let's talk about the real world. As we move from a carefully controlled lab environment towards, actual applications and potentially mass manufacturing, there's always this critical consideration, variation.
Ah, yes, the bane of many new technologies.
Right. In any fabrication process, individual devices are rarely, if ever, perfectly identical.
So how did the researchers account for this inherent imperfection, this device-to-device variability that's bound to occur when making these tiny MoS₂ devices? This is often where novel technologies stumble, isn't it?
It absolutely is. And it's an excellent and crucial question for the practical viability of any new hardware technology. The researchers tackled this head-on. They performed detailed STDP measurements on 6 separate devices fabricated under similar conditions, and as you'd probably anticipate, they observed variations in their responses.
They weren't all identical learners. No. These variations showed up in both the percentage change in conductance, basically, how much the synaptic strength changed for a given timing difference, and also in the time constants of the STDP response. These time constants define the shape and duration of that learning window we talked about.
So some learned faster or slower, stronger or weaker.
Essentially, yes. Now, this device-to-device variability, it can stem from several sources, especially when you're working with these atomically thin 2D materials. Primarily, it's attributed to tiny variations in the mobility and contact resistance of the MoS₂ channel across different devices on the wafer. These factors influence how easily current flows and thus the maximum conductance change you can get.
Microscopic differences in the material itself.
Exactly. The variability in the time constants, plus and sure, is also a direct consequence of how these underlying material properties affect the charge tunneling dynamics. Additionally, small differences in the barrier injection height at that crucial MoS₂ HBN interface can play a role.
The energy needed to tunnel.
Right. And this height can be subtly altered by microscopic defects in the crystal structure, or even by things like interfacial hydrocarbon formation, which are basically tiny trapped impurities, or bubbles as they're often called, that can occur during that precise layer-by-layer stacking process.
Building with atomic Legos isn't perfectly clean every time.
It's incredibly challenging. While the researchers obviously made significant efforts to minimize these imperfections, their complete elimination remains a major ongoing challenge in 2D material fabrication generally.
Okay, so if each of these tiny synthetic synapses is a little bit different, varying learning speeds, varying strengths, how does that impact the device's ability to act as a reliable memory and learning element within the bigger speech recognition system? Does it mess everything up?
It's the key question about practical usability, isn't it? They looked at this by quantifying the number of quantized states each device could reliably represent. These are like the distinct stable memory levels or conductance states.
Like notches on a volume knob.
Good analogy. They found this number varied between 19 and 24 distinct states across the 6 devices they measured. Now, this number directly impacts the temporal sensitivity of these synaptic devices, how precisely they can respond to timing differences, which they found was around 10-15 minors.
Okay.
Generally speaking, having a larger number of these distinct states is more favorable. It allows for finer distinctions, more nuanced learned patterns, and it improves the capability of the NSRS in classifying different auditory inputs.
So more states means better potential performance.
Right. So the variability in the number of states and the learning dynamics definitely influences the precision and range of learning that each individual synapse can achieve. It absolutely represents a potential Achilles heel for building large, reliable systems out of these devices.
Okay, so we have these individual devices, these synapses, with inherent, unavoidable variations. Some are better learners, some have more memory levels. What's absolutely fascinating here is how did the complete system, the NSRS, the neuromorphic speech recognition system, perform despite all these variations? This feels like the ultimate make-or-break test for real-world robustness.
This is indeed the critical finding for thinking about real-world application. And it was actually a very positive result. They found that, remarkably, the speech recognition system is insensitive to device-to-device variation.
Insensitive. Wow, how did they test that?
They rigorously tested this by intentionally introducing variability into their simulations. They assigned a Gaussian distribution of those STDP timescales, plus and Coriolis, across all the synapses in the system. This effectively mimicked the kind of device mismatch you'd expect in a real manufacturing run, creating a diverse population of synapses with slightly different learning behaviors.
Simulating an imperfect chip.
Exactly.
Right.
And the result, the system, even with all this simulated variation included, achieved an accuracy rate of 89.11%.
Wait, that's almost exactly the same as the 88.92% they got without the variation.
Precisely. It was similar to the accuracy rate without including device mismatch.
That is huge. It means the system can tolerate the messiness of reality.
It seems so, at least for this level of variation and this specific task. The conclusion they drew is profound and really crucial. This robustness of our speech recognition system to device mismatches is an important real-world test, as device-to-device variations are bound to exist in any fabrication process.
No.
It's a significant stride towards making these kinds of neuromorphic systems truly practical, reliable, and potentially scalable beyond just the research lab. It suggests the system-level computation might be resilient.
Okay, so let's zoom out then and really consider this so what. Why does this deep dive into 2D materials, OS2, STDP, neuromorphic hearing? Why does it truly matter for the future of computing, the future of technology, how we interact with it? The main novelty, as you've really powerfully highlighted throughout this, seems to be the demonstration and the use of the inherent plasticity of this 2D MoS₂ device. Using it to model that brain-like STDP learning rule as a synaptic memory. And crucially, doing it all within a single device and without needing any other learning circuitry.
That's the core message.
That seems like a mouthful, but it really feels like it represents a fundamental shift in how we might design intelligent systems going forward.
It truly does. The advantages that ripple out from this intrinsic learning capability are potentially profound for the next generation of AI hardware. Firstly, as we touched upon, it significantly reduces hardware complexity. Just taking out the need for separate external logic to train the network is a huge win. Imagine a computer chip where the learning mechanism is just intrinsically woven into the memory fabric itself, rather than needing this external, often power-hungry processor to constantly update and manage all those synaptic weights.
Less complex, less power-hungry.
Exactly. Secondly, this approach dramatically reduces the computational complexity and memory requirement during training when you compare it to conventional classification networks. Those often rely on really complex, iterative backpropagation algorithms.
Which are notoriously compute-intensive.
They are. They demand a lot of processing and memory. Here, that unsupervised feature learning stage learns low-dimensional feature representation. Remember those 16 learned patterns for the spoken digits.
Yeah.
That allows for a much simpler classifier at the end compared to what you typically need in those big, traditional end-to-end supervised neural networks. So if you connect this to the bigger picture, this work really moves us beyond devices that just passively store information, like traditional RAM or flash memory, or devices that just execute instructions given to them. These MoS₂ devices are designed to actively learn and adapt, to evolve their connections in a way that truly mirrors the astonishing efficiency of the human brain. It's a genuine step towards hardware that doesn't just process, but actually understands in some sense.
That really brings us to what's next then. The proposed system has successfully demonstrated this novel neuromorphic architecture for a specific machine hearing task, spoken digit recognition. But it feels like just the beginning, doesn't it? A powerful proof of concept. The paper itself suggests its versatility, saying the system can be configured to learn for other auditory cognitive tasks, such as speech recognition, speaker identifications, and so on.
Yeah, the potential is there.
So what are the immediate next steps and maybe the longer-term vision for integrating this kind of technology into actual real-world intelligent systems?
The potential for expansion is indeed vast. On the practical side, the researchers mentioned they already have that cochlea model part of the system existing as an in-house built FPGA system.
FPGA. Field programmable gate array. So that part's already hardware.
Right, which is a significant piece of functional hardware already realized. The current limitation, as often happens with these kinds of groundbreaking material science advances, lies in the practical integration step. How do you smoothly combine these newfangled memristive MoS₂ devices with standard CMOS technology complementary metal oxide semiconductor on a common substrate on the same chip?
CMOS being the workhorse of basically all modern digital circuits.
Exactly. It's the established, ubiquitous technology. Merging radically new materials like MoS₂ with mature CMOS processes is a major engineering challenge. So, a natural extension of the project, they suggest, would likely involve using two separate die.
Two separate chips talking to each other.
Essentially, yes. Two distinct chips packaged closely together, communicating very efficiently. One die would implement the memristive crossbar array, housing all these MoS₂ learning synapses for the unsupervised feature extraction. And the other die would use the well-established CMOS process for the front-end Coakley model and the back-end classifier.
A hybrid approach to start.
It seems like a practical pathway forward. But looking further out, this raises a really important question for all of us, doesn't it? Imagine the potential for truly intelligent, ultra-low-power edge devices.
Right, intelligence living on the device itself.
Exactly. Tiny sensors, wearables, maybe even parts of autonomous vehicles or robots that can learn and react to their environment in real time. Things that can recognize your voice reliably, identify complex sounds in the environment, adapt to new visual patterns, maybe even learn your personal preferences. And do all of this without needing to constantly send massive amounts of raw data up to a distant cloud server for processing.
Keeping the processing local, efficient, and private, maybe.
Precisely. This kind of localized, efficient intelligence could transform practically everything. From personalized healthcare, imagine wearables that learn your unique physiological patterns and detect subtle changes, to smart homes that truly adapt to your routines, to advanced robotics that learn directly from interacting with their immediate surroundings.
A future where intelligence is much more distributed, much more efficient.
And much closer, in principle, to how our own brains operate. Hashtag outro.
And that brings our deep dive today to a close. What a remarkable journey we've taken, really, from understanding the fundamental limits of computing as we've known it.
The von Neumann bottleneck.
Right. To exploring the elegance of these brain-inspired architectures, all enabled by the frankly surprising quantum-level properties of these ultra-thin two-dimensional materials like MoS₂. The aha moment for me, I think, is truly the ability of a single tiny device to intrinsically learn, to adapt its connections just based on the precise timing of electrical pulses.
That inherent STDP.
Yeah. And then the incredible robustness it showed, even when faced with those inevitable real-world manufacturing variations. It's just a powerful testament, isn't it, to how looking to nature, looking to the brain, can completely reshape our technological horizons and bring us genuinely closer to truly intelligent machines.
Absolutely. We're really talking about a fundamental shift here. Moving from devices that simply execute instructions given to them towards a future where devices are inherently capable of adaptive learning and, crucially, operating with potentially unprecedented energy efficiency. So maybe I'll leave you, our listener, with this final provocative thought to mull over. What could we truly achieve if we fully unlock the power of material science to create devices that don't just store information, but actively learn directly from data, mirroring the astonishing efficiency and plasticity of the human brain right there at the edge in our devices? Consider the vast implications. Truly intelligent, low-power sensing and processing for the future of AI, certainly, but also for personalized technology, for human-computer interaction, for how we understand and interact with the complex world all around us. The brain in a chip, it's moving rapidly from science fiction towards being a tangible, robust engineering goal, driven by exactly these kinds of groundbreaking discoveries we discussed today.